Okay, so this will be the continuation of the video that is going on Laplace transform of powers of n, powers of t raised to power n. So we got here, we have u raised to power n over s raised to power n, and the t here change to d over s, which is this. So and also the st becomes the u, so that is e raised to power minus u. Then from there, I can rearrange everything here as, so that becomes e raised to power minus u, u raised to power n over, now this is s raised to power n and this is s raised to power n and 1. From indices, this becomes s raised to power n plus 1 du. So this comes out that is 1 over x raised to power n plus 1, and you're having integral from 0 to infinity e raised to power minus u, u raised to power n du. Yeah, this is the real stuff we need. So this, we don't need to integrate it. It has a special form in math which we call the gamma function. So this is how the gamma function is defined. It's defined as this. So the gamma function of x plus 1 of this is equals to 0, infinity of of p. Let me use in this case u raised to power x u raised to power x, okay, u raised to power x, and then e raised to power minus u du. This is how the gamma function is defined in mathematics. So, but whenever this x is an integer, so if x is equals to n, where n is an element of natural numbers, that means your 1, 2, 3, 4, like that, in this stuff becomes this n factorial. Now I'm very sure you are familiar with n factorial. So n factorial is, now if I have 2 factorial, 2 factorial means 2 times 1. If I have 10 factorial, it means 3 times 2 times 1. So yeah, so whenever you have this particular x here, that x means a variable. Are you getting me now? It can be of any form whatsoever. It can be of any form whatsoever. But whenever you have x is equals to just a normal integer, a normal natural numbers, then this stuff equals to the what? The factorial of that number. But if it's n plus 1 here, you have the what? N factorial. The same thing occurs here now, which makes our work easier. So from this definition, this is called the gamma function. This stuff, from this definition, this stuff itself wait. This stuff, from this definition, replacing the x by n, I'll have this, I'll have u raised to power n, u raised to power minus u du. That'll be this, exactly this. Are you getting? So since it's equals to this, that means this stuff, which is this stuff is as this, right? The only difference is you have a minus u here, and that's the same thing, because a times b is b times a. Doesn't have any problem. You don't have any problem here. So that means this stuff is what? It's exactly n factorial. Going back to here, our final answer will be equals to 1 over x raised power n plus 1 times n factorial, and that gives us n factorial over x raised power n plus 1. So that will be the Laplace transform of t raised to power n. So I can, at least you can see what I did now. So what I did is I made sure that I transformed the function first of all, and it exactly looks like the gamma function, which is defined as this. So gamma function is defined as this. And since if this x is equal to what natural number, it becomes what the factorial of the number. So this stuff itself, which is this in the main question, is equals to this. So I just replace the whole stuff by n factorial. The reason why I did this is because doing this is very tedious for raised to power n. Are you getting? Well, since it already appears as a special function in mathematics, I don't have to stress myself over it. I'll just take the value. Since just you are smart, so you have to put this in a smart way. So I just change this by n factorial, then I replace it. So that would be my the transform of t raised to power n. So that means if I have Laplace of t raised to power 2 to be 2 factorial over s raised to power 2 plus 1, and that is 2, because this 2 times 1, which is 2 over x raised to power 3. That will be my answer. Another one, if I have Laplace of t raised to power 3, that will be 3 factorial over x raised to power 3 plus 1, and that is 3 factorial is 6, and here is x raised to power 4. So that will be my answer on this. Also, there is a connection between the powers of t and a constant function we did before. You can try that. So think of it. Let's assume I have k here. For example, you know Laplace of k is what? Is k over s. So I can do it in this form, in the sense that this is a constant, and we know integral in constant can come outside. So this can become the Laplace of 1, because this is k times 1. So since this is k times 1, I brought, it's a constant, k is a constant here. So I brought the k outside. So I'm left with 1. But I know 1 in mathematics is defined as a variable raised to power 0. That is what 1 is. T raised to power 0 is 1. And it's any number, any stuff whatsoever raised to power 0 is 1, except 0. So I know this 1 is defined as what? As t raised to power 0. I can replace this 1 by t raised to power 0. So the Laplace of this is equals to the constant outside, and I have t raised to power 0. This stuff looks exactly like this, and I can use my formula, and you see that it will be the same what we got before. So this is k staying here. What is 0? That will be 0 factorial over s raised to power 0 plus 1, and that is k. What is 0 factorial? 0 factorial divided in mathematics is 1. So that is 1. Let me say 1. And what is 0 plus 1? 0 plus 1 is 1. So that is s raised to power 1. And that is s. And everything becomes k times 1 is k over what? Over s. If you remember the former result, we also got the same k over s. So that's how it works. So it's very simple. I think let's check the other one. Let's check the other function, like trig functions. Let's check for sine. Let's check for cosines and all that. check this out. Laplace or sine kt. So the k here is a constant. We want to find the Laplace transform. We know here this stuff here has a very beautiful way of representing it in maths. So for that case, I'll introduce in a new way, which is this way. Now we have what is called the Euler's formula on sine and cosine. The formula says this. The formula says if I have Euler's formula, if I have e raised to power I kt, that is formula, so is equals to cos kt plus I sine kt. That is Euler's formula on cosine and sine. So it brings cosine and sine together. We can use this form to change this sine kt here to something in another way. And how do we do that? So this expression now is what we call a complex number. This stuff is a complex number. And in complex number, we have two parts of complex number. This I you are seeing here is called the I, is an imaginary number. And the I has a square root of -1. But that is only there, but that is the value, or that is the actual mathematical representation of I. The cosine here, now before I write the cosine, now in complex number, this is a complex number. If I have this, the A here is called the real part of Z. Let me write it in words. The real part of Z. Real part of Z. That is what this A is called. The B part is called the imaginary part of Z. It's called the imaginary part of Z. That's what it's called. So exactly the same thing happens here also. So this sine kt now, this sine kt you are seeing here, it is an imaginary part of this. Imaginary part of this. Because this stuff itself is also a complex number. So that means this part is the imaginary part, and this part is the real part of this. Are you getting? So writing this representation now is very useful in solving this, rather than doing the normal way. Because doing the normal way can get us into trouble. It takes more time, but this is very easier to solve, very easy to solve than solving this directly. So we'll go to that. So I think you can see this. Then let me clean this. So from there, you can clean this side, and so my Laplace of sine kt. Now I'll replace this. First of all, I have this. I've now the definition of Laplace. So it's e raised to power minus st. The function itself sine kt, and you have dt. But can you replace this by what? By this, the imaginary part of I kt dt. Now this im is called the imaginary part. I can think of it as a as an operator. I can bring it out of this integral. So the integral look exactly like this, minus st and then e raised to power I kt dt. So this im here is what I brought out here. So that means I'm only concerned with what is here. If I'm true, I will not take the imaginary part of everything here. That makes more sense. So, but this is an indices that I can take. If you look at this, it's an indices that you can bring together because they have the same base. They have the same base. So from indices, this can become the t is common. The t is common. So this can become s minus ki and I have t. So you can see the t is common. First of all, I added them. Let me write one by one. I added them. First of all, I have minus st plus IKT. You know why this is? Because in maths, when I have this of m plus n, that's what I have. So that's why I added these two, and that becomes imaginary part of. Now the t is common. I can say it can become this. So I brought out minus. When I brought the minus affect this. So the sign changes to minus. Minus and this is still minus x. And minus times this is what? Is plus. So I also brought the t outside. So this is more meaningful now. But to avoid stress, so going from here, this stuff is exactly like what we did before. If you remember in my last video, I said let u is equals to, now in this case I'll reduce it. So x minus ki t. Can you look at that? Doesn't mean anything. I can say okay, my du dt here is my s minus ki. Doesn't mean anything, and also my my dt in this case, my dt here can be equals to du over s minus ki. My du can be equals, my dt can be, so I brought this dt here, brought this here. That is du over x minus ki. Doesn't mean anything, just replace everything. So this is an operator. I've said before, it's an operator. So imaginary and this infinity. Okay. Before I go to that, I have to check out the boundary, but I think it's also the same. So as t is going to 0, u also goes towards 0. Goes to 0. 0 times this is 0. 0 times any number is 0. And t goes to infinity also times infinity also explodes to infinity. Are you getting? So I can do the same thing here. So I can also turn everything to the imaginary part of this and this, and so that becomes e raised to power minus ut, sorry, e raised to power minus u and then du over s minus ki. That's what that becomes. So that becomes this, and from there, so I can bring this part outside. um, 1 over s minus ki. So I'll have infinity 0. And in last class, in last video, we did this in last video that the integral of this